This virtual field trip is focused on some outcrops of the Swiss Jura, where the mountains are characterized tectonically by low-angle thrust fault with multiple ramp-flat trajectories. These virtual field trips target people involved in a reservoir fracture study, but not familiar with geology. So the goal is just that of giving some basic concepts about the fractures network affecting a reservoir. Because fracture system exposed, affected by late-acting processes like unloading and weathering, are bound to be different from the fracture systems of the reservoirs, which are located at several thousand meters aerial depth, caution must be utilized with what we can see on outcrops. However, outcrops can certainly give some insight on the possible characteristics and complexity of the fractures network affecting the flow path in the producing fields. So, while remaining in the Western Alps area, we move from the former two field trips located in the Helvetic nappes to the internal Jura outcrops of the four land units located about 100 kilometers northwestward. Willing to focus the attention on about the same kind of rock, to appreciate the different characteristics of the fracture network in different structural contexts, the big jump of 100 kilometers to the Jura Mountains is requested because the carbonate rocks outcropping in the Helvetic nappes dives northward below first the Prealps and then the Molassa units to outcrop again northward of the Neuchâtel Lake. So, going back shortly to the former virtual field trips, we can remember that the outcrops of the Rowell Pass and the Larette de l'Argentine belong to the Cretaceous-Urgonian carbonate platform and are included in the Helvetic nappes. They were subjected to very strong stresses being incorporated in the accretionary prism during subduction. The observed fracture intensity is very high in both the locations, but with different intensity that mirrors their tectonic history. In fact, the Helvetic nappes represent the deformed sedimentary cover deposited on the southern edge of the European continental crust. They represent the last elements incorporated in the accretionary prism during subduction below the African plate. One of the final steps of this complex process was made by the overthrust of the more distal ultra-Helvetic units on top of the Helvetic domain at that stage still unfolded. After this event, two further stages of compression affecting the Helvetic domain were recorded. A first thin-skinned tectonic stage producing faults associated with the thrust at the base of the nappes. The result of this nappe stacking is illustrated in the bottom left corner sketch, where the Helvetic sequences results vertically repeated several times. From the highest southernmost more allochthonous nappes, the Wildhorn nappe reported in yellow in the sketch, to the lowest northernmost para-autochthonous nappes, the Morse nappes, reported in green in the sketch. In fact, the nappes from top to bottom are in relation to their original paleogeographic position, that is from south to north. Therefore, these two nappes are characterized by a different both paleogeographic origin and transport distance due to a different original position from the European plate margin. A second stage of compression happened later when the nappe stack was updomed and folded on a large scale. This stage was associated with the progressive exhumation of the Alps and rocks cooling and affects altogether the Helvetic nappes. So let's go back very shortly to the former field trips. The outcrops located on the southern flank of the Schneiderhorn Peak, observed in the Rohwil axial depression in the former field trip, belong to the more alloctonous yellowish Wildorn nappe, which underwent strong stresses during the thin-skinned tectonic stage, likely stronger than the stresses which underwent the greenish mortal nappe, the lowest northernmost nappe that is estimated as para-autochthonous. The different stresses are in relation to the different original distance from the European plate margin that was larger for the overlying Wildorn nappe. Accordingly, the fracture intensity appears very, very high. From this image, we can infer how the fracture intensity can be high in a reservoir. With the fractures spacing in the order of few centimeters. A scenario that could lead, according to Nelson Plot, to the classification of this kind of reservoir as a type 1 or type 2 in relation to the rocky matrix contribution to the storage and flow capacity. On the other hand, the outcrops located on the northern flank of the Lavette de l'Argentine, the so-called Les Miroirs de l'Argentine, observed in the former field trip, belong to the greenish mortal nappe, the lowest northernmost nappe estimated as para-autochthonous, being the original distance from the European plate margin smaller than that of the Wildorn nappe. Accordingly, the fracture intensity, although quite high, appears to be lower than that observed in the former outcrops of the Wildorn nappe. In fact, looking at Les Miroirs de l'Argentine from north, as illustrated by this photo, the widespread presence of fractures on these very steep beds can be glimpsed. Confirmed by a closer observation of the upper part of the rocky wall, as well as in the middle part of the rocky wall, as well as in the lowest part of the rocky wall. The fracture intensity is definitely quite high, with the fracture spacing in the order of meters, so less intense than that observed in the Rohwil axial depression. scenarios that could lead, according to the Nelson plot, to the classification of this kind of reservoir as type 2 or type 3 in relation to the rock matrix contribution to the storage and flow capacity. So let's move now with a big jump of about 100 kilometers north of the Neuchâtel Lake, where the carbonate platform outcrops again, but in a quite different tectonic context that has a different impact in terms of rock fracturing. This regional cross-section, north-northwest, south-southeast oriented, goes from the Prealps and Molassa Basin in the south to the internal Jura Mountains in the north. In this later area, the tectonic context is made by a low-angle thrust fault with a multiple ramp flat on which several hinterland verging thrust nucleate. The main décollement level is in the Triassic evaporites. The area is so characterized by east-northeast to west-southwest trending anticlines, synclines, and low-angle thrust that are oriented, as expected, perpendicularly to the main compressional stresses in charge of the alpine orogenesis. We are going to focus our attention to the area between the Traverse Valley northward and the Neuchâtel Lake southwards. In particular, we are going to focus the attention on the so-called Nouvelle Saint-Cyr anticline, highlighted in the cross-section top right corner, in the structural map on the left, and on the topographic map on the bottom right. This anticline is eroded at the top, where therefore outcrop the older Jurassic rock, while the younger Cretaceous rock eroded at the top are present on the flank of the anticlines. This anticline is bordered north-northwest by the Val de Traverse thrust and is affected by several tierce faults running across the strike of the belts as illustrated on the geological map. Initially, we are going to focus our attention on the so-called Creux du Vent, that is a natural rocky amphitheater, approximately 1,400 meters wide and 150 meters depth. It formed because of erosion related to the melting of glaciers acting on the Jurassic carbonate, affected by several tear faults on top of the anticline. These elements, altogether, caused the collapse of the easternmost part of this anticline, giving us the opportunity of observing, let's say, the interior of the anticline. So, looking at the Creux du Vent from east-northeast point of view, we can see, as depicted by the cross-section, the anticlines collapsed at the top, verging north-northwestward on top of the Val de Traverse thrust. Being in this location, the Urgonian carbonate platform eroded, outcropping just in the northern synclinal, we are going to observe the fracturing in this structural context, mainly in the Jurassic Formation. They are made by carbonatic layers of a variable thickness and characterized by different platform interior rock types: mudstone, wexstone, techstone, greystone, with bioclastics, pteloids, oid, and oncoids. This formation thickness range between 140 and 160 meters. Let's have some view of these outcrops. The impact of faulting and folding on fracture is conditioned by the different rock characteristics on which they are acting. Considering the bedding, we know that joints generally occur at high angle to layering, where commonly terminate at mechanical bed boundaries. These joints form parallel sets with the spacing generally wider in the thicker beds. So, for a given stress, we expect a reduction of the fracture density with the increment of the bed thickness. Considering lithology, we know that brittle rocks, characterized by low porosity and fine grain size, are more prone to develop fractures with respect to high porous, air or ductile rocks, which are more likely to deform plastically. As illustrated by the plot, dolomite, for example, is more brittle than limestone, and for a given stress, the fracture intensity is expected to be higher in relation to the dolomite content. Fractures observed on the outcrop support this view and show a substantial difference in the number of fractures for different rock. For example, in the outcrops illustrated on the left, the stiffness light plays a role in the contrast observed of fracture density between the charred nodules and the surrounding limestone. In fact, the stiffer, more brittle rock should show a higher density of fractures than a less brittle rock. The different fracture intensity can be observed also in the different layers in the outcrops illustrated on the right, in relation to lithology, grain size, and thickness, with the thinnest limestone layers affected by the closest fracture network, as highlighted by the cementation. The impact of faulting and folding is so conditioned by the different rock characteristics on which they are acting, and consistently we can observe also in this outcrop that the higher fracture intensity, illustrated by the high P10 values, is located mainly in the upper part of this bed sequence, that is characterized by the thinner layers. However, the fracture intensity appear to be relatively low if compared with those observed in the other two former field trips, and probably they hardly reaches in this context the percolation threshold at a large scale. So this is a scenario that could lead, according to the Nelson plot, to the classification of this kind of reservoir as type 3 or even type 4 in relation to the fracture network 3D continuity, a continuity probably reached in this kind of context only just close to the fault zones, in the damage zones. Now, as the last step of this virtual field trip, let's move from this fascinating landscape to the close Traverse Valley. Located just northwestward, where the Cretaceous Urgonian carbonate platform formation, our leitmotif of these virtual field trips outcrop, just below the Val de Traverse Trust. The reason to move to this location is that here we can visit the tunnels of a very old asphalt mine, proving the Urgonian carbonate formation as a real hydrocarbon reservoir. This old mine, named La Presta, has a quite long story. The presence of asphalt-bearing rock in the Traverse Valley was discovered in 1711 by a learned Greek named Erinis, who started the mine exploitation in 17 1813. After the death of Irénée de Renice, the exploitation of the mine was interrupted, to be resumed in 1833. Among the several entrepreneurs involved in this mine, we can mention also Philippe Souchard, that could sound a little strange, being Souchard also the famous founder of the well-known chocolate factory that bears his name. The exploitation of the mine was initially performed as open pit, and then from 1869 by tunnels. It is estimated that at the time of the closure of the mine, the total length of the excavated tunnel exceeded 100 kilometers. In 1873, after several changes of ownership, the mine came under the control of a new company named Neuchâtel Asphalt Company Limited, with a registered office in London. The extraction reached the maximum production in 1913. In those years, large part of the asphalt production was exported in Europe and overseas, England, America, and even Australia. It was at those times, before the First World War, that the mine of La Presta was considered the most important asphalt deposit in West Europe. The mine was closed in 1986, but now is possible to visit the galleries and the related museum. Walking through the tunnel of this mine is certainly suggestive. Thinking about the hard work of the miners for more than 250 years. However, the poor light in the tunnel does not allow to make a geological observation, so we can make some consideration by referring to some work published at the end of the production history of this mine. Asphalt deposits occurs in two different formations. In the last bioclastic oolitic sequence of the Hautérivian-Barrémian formation, named Pierre-Jean de Neuchâtel, and above, in the rudest bioclastic phases of the Aptian formation, named Calcaire-Urgonian du Jura. However, although several levels are impregnated, only two horizons belonging to the Urgonian were considered economically interesting. They are the Mont Blanc, that is the main deposit. Its average thickness is 4 to 6 meters, with 9% of asphalt content. On top of this Mont Blanc, there is the Petit layer, the secondary deposit that is of irregular and variable thickness and with a lower asphalt content. It was not exploited, if not locally. The asphalt-bearing rock is subdivided into soft, medium and hard, characteristic that is function of the cementation of limestone. Here are some examples. The source rock is unknown. The hydrocarbon migration is interpreted to be occurred in two steps. Along the time the Jura Mountains building, a first migration before the Jura Mountains folding and faulting. The hydrocarbon would have been trapped stratigraphically or more likely by a structural trap in relation to a paleo-high kind of Jura Mountains precursor. A possible second migration settlement during Jura Mountains faulting. A biodegradation and oxidation following the Jura Mountains folding and thrusting. Some consideration can be made about the fracturing affecting the reservoir rocks along the time. During the first migration, the rock fracturing was likely very low because of the very fair stresses the rock had suffered. During the second migration, the rock fracturing was likely more significant according to the increasing stresses the rock had suffered. After the folding and thrusting, the rock was likely to have reached a quite high fracture intensity, also in relation to the proximity of the asphalt-bearing rock to the Val de Travers important thrust. In fact, the presence of a fracture network with a very high permeability has represented the main concern along the mine exploitation. It was necessary to face the high influx of water to prevent the flooding of the tunnels. The presence of open fractures not plugged by the asphalt supported the idea that the fracturing was contemporary or later than biodegradation and oxidation. Here you can find a short list of papers to refer to if you are interested in investigating more in depth the geology of this area.